Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And I'm delighted to be here and giving this talk in front of Luca and all of you to tell you about a lot of the fun we've been having learning about machine learning and how ideas from functional programming can have an impact. Now, this is, I said when I agreed to give this talk that I would really talk about my current work, and I wasn't going to try and review what we had done, Luca and I, many years ago. And so is there a connection between this and what I did with Luca? Well, so one aspect, this is a playful thing, in that Luca has always been someone who I think has been an adopter of sort of mainstream technologies, maybe ahead of academics or other researchers like Dave last night reminded us about Luca's early adoption of Macs. And he was also an early adopter of Microsoft Word and wrote his papers in Word, which I thought was pretty cool when everyone else was using LaTeX. So this work is like taking, Tabular is taking these ideas of probabilistic programming for doing statistics and putting them into Excel. So we're kind of going for the sort of mainstream product rather than sort of going for developers. Another connection is that I was so cross with Luca for stealing SPI. We had this SPI language, Martin and I, and then he had this system with Andrew Phillips, SPIM. And we're always a bit disgruntled about this. So, well, not... exactly, it's not SPI, but it's still called, SPI, it starts with SPI. So anyway, our language... You stole the S. So we've stolen his name. So we heard yesterday about fun, the type theory in his paper on understanding types and data abstraction. And so we stole it for the name of our language, fun, which is a probabilistic functional language that I'm afraid has got nothing to do with Luca's fun. But we thought we would steal the name. Okay, so what is this about? So what I'm going to do, first of all, is give you a brief idea of how probabilistic programming can represent statistical inference. I'll say a bit about the probabilistic programming languages that currently exist, and then I'm going to explain how we took those ideas and have embedded them inside Excel with the attempt to take them to the sort of large class of data enthusiasts who are very comfortable using Excel. They've got huge amounts of data in Excel. They're kind of not professional developers, but they're people who are quite capable of writing scripts and do quite sophisticated things in Excel. And we like to be able to give them the power to use probabilistic programming to learn from their data directly within Excel. Okay, so what I'll do is describe a sort of little probabilistic puzzle on how we learn from data. And so it's a murder mystery. So we have there's a body in the room. I think we've got some English country house, and there's been a murder. Think Cluedo. And Alice and Bob are in the frame. And for whatever reasons, we think it's actually most likely that Bob done it, 70% chance. And we think that if Alice's preferred weapon would be a pipe with 97% chance, and Bob's preferred weapon would be a gun. So let's see if we can represent that as a bit of code. So this is the basic idea of probabilistic programming, that we write some code, and this is in a sort of, a couple of Boolean variables. So we flip a coin to indicate whether Alice done it or not. So she has a 30% chance of doing it, and if this is false, it's Bob has done it. And then, has a gun been used or not? Is it a gun or a pipe? Well, we look at whether it's Alice done it or not, and if it was Alice, then we flip this coin, because there's only a 3% chance she'd use the gun. Otherwise, we flip the 80% coin. And so overall, you would get this distribution over the two outcomes of who has done it and which weapon they've used. So you see the most likely thing is, a priori, before we've observed the scene, it's most likely that Bob has done it using the gun. Now, suppose we actually get to the scene and we discover a pipe. So this is the point where we condition the probability distributions that we've defined with some evidence. Right? So far, we've got two unobserved variables, who has done it and which weapon has been used. And that's what this chart is showing. So now suppose we found that the gun was used. So we condition the, whoops-a-daisy, we condition the distribution. And we can do that in code by adding a constraint. essentially an assertion that the withgun variable is false. So this essentially rules out the runs of the program where withgun is false. And so we'd end up with this sort of chart, where we sort of chopped out this probability distribution here, and then we renormalize these two bars. And now we see that the situation is flipped around completely. Now it's most likely that Alice has done it using the pipe. I've been talking about runs of the program. So the sort of naive understanding of these programs is you just run them many times, and you maybe rule out any runs of the that violate the constraints, and then look at the results. And that's how you can sort of compute these histograms, these charts. And that's a naive thing, and you can formalize that. And then there's also a whole great panoply of inference algorithms that can do a much better job than just naively running the programs many times. And the idea of probabilistic programming is really to let you build these models by sort of taking a programming language, say a C-like language, or whatever language you like, actually, and you need to add the ability to draw random numbers, and you need to add the ability to place constraints to actually condition, on unobserved variables once they've actually been observed. And finally, you need some way to indicate which distributions are to be inferred. And the alternative to doing this would be, which is what a machine learning person would do, would be perhaps write these algorithms from scratch. And the thing is that community has been busy working on this for a good long time. As I say, they have many algorithms, and we really got to the point now where you can build quite practical compilers that can take a description in a language with these sorts of features and compile them down to efficient inference code. So this has been done for a while. So Bugs actually started out about 20 years ago in Cambridge, and it uses a kind of sampling, and it was a probabilistic functional language developed in the stats lab at the university here. And there's been a bunch of others. The infer.net system, which we added this fun component to drive it from F#, has been developed in this lab, but there's many others. And if you want to go look up the semantics, Gordon is one of the, where's Gordon? Gordon was one of the pioneers in his work with Claire Jones, and Dexter Cozen, mentioned yesterday, was probably the first person to do a nice formal semantics of probabilistic languages back in the 80s. And Prakash has done a lot of work. And the semantics of the various languages we've developed over the years have been based on this. But I'm not really going to get into formal semantics today, except to allude, if you're interested in that we've got lots of papers with theorems if you want to see that. Kathleen Fisher, I'm not sure if he was she's a co-author of yours, Luca, but she did send her regards. She couldn't make it to this event. But she's currently at DARPA, and she's heading up a program there called PPAML that is basically sort of seeing that we're at a point where high-level languages for machine learning are a bit like where high-level language for any sort of programming were 50 years ago. And that DARPA is putting a lot of money into sort of in research in this area. So it's rather a hot topic. Now, what I'm going to talk about specifically is languages for what are called graphical models, which is a particular case of probabilistic programming. And I want in this slide to give you an idea that it's really a kind of functional programming. And you can think about quite a sophisticated machine learning model as programming. And the thing, and what I'm going to give you two different interpretations of this program. But first of all, let me tell you the problem. So we've got the master chief up there, and some years ago Microsoft launched Halo, and the problem was you've got many, and in particular the online version of Halo. So the problem is you've got many players in the online version of Halo, and you want to matchmake them to have dueling parties. And you want to matchmake people who are roughly about the same kind of level of difficulty. That's where most people get the most fun, if they're not being completely hammered by someone who's much better than them. So how do you do that? I mean, so intuitively, players have got a skill in the game, and you'd like a number, and let's say it's a number between nothing and 50 with mean 25. And you want to sort of figure out how skillful people are. So how do you do that? I mean, it's not as if everyone has played everyone else, so we don't have a rank ordering. We've got rather a sparse comparison of the players in the tournament. So let's see. So the way it works is that we define a sort of program, this graphical model, that would generate the data that's observed, and then we can sort of run it backwards to infer those skills that are not directly observed. So what you do observe is when players come together. So in this case, I've got a simple situation where the observations you have is of binary matches between players, and you can see whether which of the two players has won. So up here, we say, so we've got a sort of a collection or a table of players and a collection of matches. And these boxes, this is what is called plate notation in the machine learning community, and it's basically like a map. So the code that's inside the box is to be replicated some number of times for each of the players. And so what this is doing, so it's a graphical model, and there's two kinds of nodes, and the circle nodes are random variables, and these square nodes that link the circle nodes are what are called factors. And in functional terms, they're really just computations that take the current values, or the current values in this run of the random variables and produce some other random variable. So what this is saying is what I just did. What I just said, that the skill of each player is a random number with mean 25 and the standard variance 100, which is the same as standard deviation of 10. So it's roughly a number between nothing and 50, sort of comped around 25. And then what this part of the program is doing is picking up. So it's saying for every match, we look up who are the two players playing. So these blue circles are actually inputs. So they're not actually random variables. They're set by the data. So we pick up the indication of who is playing in a particular match, and then these factors basically look up the skills of each of the two players, and then we want to compare them. But actually, it's too strong just to say that the person who's going to win is the one who has the highest skill. Instead, we want to add a bit of random noise because there's often there's this element of chance in many games, and also people vary day to day. So what we do is we have a performance which is like of each of the two players, which is like a noisy copy of their skills, and then which is obtained by just doing a Gaussian draw with the mean being the skill, and we add another sort of standard deviation of 10. And then we compare them, and then that produces the output to indicate who has won. So that's the forward run. So if you imagine running this program, giving if you had the fixtures of a tournament and you ran it forward, it'd be sort of like a fantasy tournament that would first of all choose the skills at random and then produce the outputs based on these formulas. Not at random, I mean based on the skills that were chosen. And so what we actually want to do is run it backwards, because we don't know what the skills are, but we do know what the outputs are. So that's the inference step, where we do the observations, a bit like observing that the weapon was in fact the pipe. And we can think about these orange output variables as being constrained, being observed by the actual data in the data set. And then that's the point where we would use an inference algorithm to actually infer what these unobserved random variables are. So that, in a nutshell, is how you use graphical models. And they're pretty amazing, I think, in that this is a formalism that can do a whole lot of machine learning tasks. So there's a few other models. And it could do things like regression, cluster analysis, topic modeling, and so forth. And I don't have time to try and explain what those things are if you don't know. I mean, what attracted me to this was that the guys in the machine learning group here had built this cool compiler that had a really weird input language. But the really cool thing about it was that it was really broad. There's zillions of algorithms or models that you can define using it. And so what we knew for the last few years is trying to understand what they were doing, and first of all come up with this. You used F# to define the models, and then now in Tabular we're defining these models using inside Excel. And so that's a link to the infer.net page, and credit to John Wynn and Tom Minka, who are the leaders of that project. So in this talk, I want to do these things, to describe Tabular, and I've said already that we're aiming at the sort of the data enthusiasts. I mean, infer.net is directly sort of aimed at machine learning PhDs and sort of maybe high-end sort of sophisticates like data scientists. And we're trying to sort of take probabilistic programming to the masses, which is challenging, but I think there could be a great payoff if we could pull it off. And there's some guiding principles So the key one, which I'll explain in the next few slides, is that instead of thinking about the probabilistic program as being something that's sort of completely separate from the data, which is the case in all the prior probabilistic languages that I know of, all the ones I put up, we say, well, actually, you can't do machine learning without data. The data is going to have some sort of relational description. And look, the relational description corresponds really closely to the plate notation that I showed you. I had a plate for all the players, and I had a plate for each of the matches, which sort of corresponds to the table of the table of players and the table of matches. And we asked, well, hey, I wonder if we could annotate the relational schema of the data with probabilistic expressions and use that as a way of writing the programs. And we think if we could do that, then this would fit really nicely into Excel, because these days Excel actually has a relational data model built into it. So it already has that. It already has a UI for defining the relational structure of your data. So we figured, what if we added a little bit of functional programming actually to the Excel data schema, and then that led to Tabular. I said you always have to define what it is you want to infer, like whodunit, or what the skills are. And we've got two ways of doing that. One is by querying for latent variables, the sort of gray variables, but the other one is for missing values. So sometimes you haven't seen all the matches. You've seen half the fixtures which are observed, and the other half are unknown. And often that's what you want to predict, because you maybe want to make a bet or something. So the second way that we can do inference is by filling in blanks, and I'll show you that in a moment. And at the very end, I'll say a bit about autosuggestion, because I think at the moment, Tabular is quite usable. Probably by people who are at this end of the spectrum at the moment. Those are our current users. But to get down to this spectrum, we need some way to autosuggest models. And I'll say a bit about some ideas for that. OK, so now let me go through the same example, but now in the setting of Tabular. So we have a small data set here of players. We've got Alice, Bob, and Cynthia. And we've got just a couple of matches. So this is Alice has met Bob, and Alice has lost. And Bob has met Cynthia, and she's lost. And so the schema would look like that. And these are all sort of snapshots of what we'd have in Excel. So you could have a schema like this. The name, each row in the players table has got a name that's a string, and the matches have got who is one. And then these links are just indicating that this is a foreign key relationship, which is actually supported inside Excel. So it's saying these are integers, but they're actually foreign keys into the players table. So here's how we annotate that schema with probabilistic expressions. And in so doing, we get back to the graphical model I showed you to start off with. Okay. So on the players, so if you like, I should point out there's been a shift by 90 degrees. Okay. The data tables, if I go back here. Sorry, this might be confusing. These data tables are laid out like that, with along the column names are along here, and when we get to, I'm going the wrong way. When we get to the schema, the column names are laid out vertically. Okay, so moving back. Right, so here we've got a column name in the original table, and so these two columns in this sort of schema correspond to the original schema, and the new stuff is over on the right. And the color coding just corresponds to the three kind of annotations that we place upon the columns in the original data set. So over here on players, we just declare that the name is an input, meaning that we're not going to try and predict it, but we may make use of it. In fact, we don't use it in this case. And then we have a gray column labeled latent, which is not present in the original database, but we want to be able to predict it, and we have it's a sort of part of our model. So we just say Gaussian to indicate how the skills are defined. And then down here, we've got the matches table, and we've added a couple of new latent columns to the matches table, which are the performances I spoke about, the noisy copies of the skills of the two players. And we say player1.skill is just dereferencing this foreign key and getting the skill that we defined, adding some noise, and then finally we have an output perf1 greater than perf2. And in the original program I showed you, remember for Cluedo, I explicitly had to put in this observe that the pipe had been used, and that's the typical thing you have to do in most other probabilistic programming languages. And a nice feature of Tabular is you don't need to do that. Simply having labeled this as an output, just implicitly what it means is that the probabilistic model, or this graphical model that we get from this, has these output variables observed by or constrained to be equal to the actual data if they're present. So we just do that implicitly. There's no need to have to put those extra observes in. Okay. So the different kinds of querying. The first one is by latent column, which is like filling in those, lighting up those kind of gray columns. So if you have that data and run it, what Tabular is going to do is infer some Gaussians for the Gaussian distributions for the performances, but most interestingly, we get the performances for the skills. I mean, in this case, you can see Alice has lost to Bob, and Bob has lost to Cynthia. So as expected, Bob is still around about skill of 25, but Alice has got a lower skill, and Cynthia's got a higher skill. And note also that the variance has dropped significantly. So before we had a variance of 100, but now we've dropped rather, which basically means it's a much tighter Gaussian. You know, it's much more likely to be, you know, close to 22. And then the other mode of operation is query by missing value, where, you know, we want to predict what's going to happen if Cynthia, in this case, where Cynthia meets Alice. So this is blank, and so what Tabular will do is fill that in. And so Bernoulli distribution is a coin flip with 85% chance of coming up true. So because Cynthia's got a much higher skill in the model than Alice, it's much more likely she's going to win that. So in a sense, that's all there is to Tabular. You know, you put your data in. In fact, I think that is on a slide. You put your data in. You have your scheme of the data. You have to have in mind a model, a probabilistic model of your data. So you know, such as based on these hidden skills. So you can express those hidden skills by adding latent columns, and then you write your models for the latent output columns, which is really just those little probabilistic expressions we define. And then Tabular will step in and infer the latent columns and also parameters of the table, and will predict values. And so...
And could you just say, so do you learn these values, or do you infer them symbolically by... So these missing values, these distributions, these Bernoulli, are they done by using reinforcement learning or some simulation techniques, or are they done in a symbolic analytical way?
They're done. They're done by statistical methods. Either by sampling methods, where you generate lots of parameters and then observe the data, or alternatively, there's these what are called message passing methods, where you have the graph and then you have an approximate distribution. So for each of the going back a little, in these message passing methods, they really exploit the structure of the graph here, so that what you do, it's essentially a constraint satisfaction problem. That you have so the whole graph is defining a joint distribution over all the random variables, and the joint distribution is intractable to work with when you've got lots of data, because it's just so big. So instead what they do is they approximate by saying, well, let's look at the marginal distribution.
Like a Bayesian network?
A Bayesian network is a special case of a graphical model. So you have a marginal distribution in each of the random variables, and then you have a series of cycles where you try to hit a fixed point by sending messages around based on the local structure of the graph. But I like the measure theory. I don't want to get into that in this talk. And in fact, that's not a contribution. I mean, in a sense, that existed, but we felt it had a poor user interface, and so we're trying to use language techniques to make it better.
How can you get such a reduction in variance with just two matches? Is that something I'm missing here?
That's a good point. It's possibly a typo in the slide. If Gordon does it, there probably isn't enough data. I'm not sure about that. It could be a. Let's leave it at that. Partly because it's a tiny example. The more interesting thing is when you look at what I was going on to next is when you look at larger versions. So one of our first users, one of the machine learning guys in the group, who was wanting to study, he wants to do sports predictions using the underlying system infer.net, and he's been a great adopter of Tabular. And so he had a rather more complicated model. So here he was looking at American college football, and there you start to get a hierarchy because you have you have teams which sort of correspond to players in the original model I had, but teams are grouped into leagues. And leagues, I mean, the fact that you're in a league gives you some information because some of the leagues are better than others. So as soon as you want to have a model that can, after it sees some teams in one league, or once you have other teams in the same league as you playing, you'd like that information to affect your own skill. So in his model, each league has got what he called a skill modifier, and then each team has got an individual skill, and then the actual skill of the team is the sum of the individual skill and the modifier. And then he has a match model, which was like the one I showed you, except it also has a home advantage variable. But then otherwise, he computes the performance of the two teams and then adds them together. And so then over here, he's able to actually do a nice job of making predictions about the quality of the teams based on the based on this model. In fact, he's got the point is that I showed you a very baby example, but he's got you can do more sophisticated ones that actually are as good as using Infer.net directly. Okay, so what I would like to do is say a little bit more about the language features and tell you in the time remaining about, I suppose, from a programming language point of view, the unique feature of Tabular, which is this construct called of model expressions, which I'm interested in feedback on because I've had this hunch that it's like a sort of module mechanism or a kind of object mechanism. So, yesterday's talk made me intrigued about that again. So I'd be very interested in feedback on this. So firstly, I want to give you an idea about a feature I've not told you about, which is parameters of the model. So think about linear regression. So you've got a bunch of blue points, and you want to learn this this red line. And the parameters of the red line are the slope and the intercept. So it's given by this. Y is ax plus b. So we've got the slope a, and we've got the intercept with the axis b. And then we also have some noise. And the noise is Gaussian distributed with a certain variance. If we want to represent that in Tabular, it looks like this. Well, what's the data? We always start from the data. The data, we use the xy pairs. So that's down here. We've got the x, y pairs. X is an input, and we want to produce the output. We describe the model. We've got an intermediate variable z that's ax plus b, and then we add the noise to z to get the y. But what are the a and the b? Well, they're outside the loop. So far, let me bring up the graphical model. So far I showed you that in the TrueScale model, everything is inside the two loops. The plates are like loops over the data, and all the random variables are sort of associated with a data point. Well, it's often very useful to have parameters that are outside the loop, and that's what this is illustrating, where the parameters a and b of linear regression are outside the loop. And so we had input, latent, and output are the keywords that say that you're inside the loop, but we also have hyper and param, and hyper is just a deterministic constant outside the loop, which in this case is just 0. And a and b we declare as being params, which means that they're outside the loop, and they have particular models, so they're just chosen randomly. And so these are like the priors of the model. So we don't know what a and b are, so we just choose them randomly using a Gaussian. And this is somewhat arbitrary, so I don't particularly want to defend the choice of 0 and 1. That would really depend on the situation you're in. But then, given those priors, you have a plate that actually will modelly observe data, and then that will have the effect of pushing back to what A and B are most likely. So sort of the standard least squares algorithm corresponds to this. So just by writing this forward process, we would, when you compile this to inference code, you get something that's similar to the least squares algorithm. But the point is we have stuff outside the loop. So now, if we go to the tabular language, here's its grammar. A schema is just a list of tables. So little t are the names of the tables, and big T are the descriptors of the tables. And each table has got a series of columns named C1 up to Cn. They have some types that, generally speaking, are scalars or arrays or vectors. I won't get into them. And that would be, so if you just did that, that would just be, a particular way of writing a relational schema. But we have these annotations, and that's the sort of tabular sort of contribution. And so far what I've shown you is annotations that look like these, where, so there's hyper and param, which are outside the loop, and input, latent, and output are sort of within the loop, within the map. And these M's have always just been simple probabilistic expressions like Gaussians or conditional expressions or sums or whatever. But what is interesting is that actually is where you have full model expressions, where a model expression is defining some material that's to go outside the loop and some material that's to go inside the loop. And this is what I mean by the module. It's almost like an object where there's a sort of constructor that's sort of outside the loop, and then there's a sort of instance that gets called, for every entry within the loop. And so a model expression M defines, or more formally defines two things. There's the part that's outside the loop, which is called the prior, and it's a distribution over some parameter W, which in the linear regression example was A and B. And then there's a part that's inside the loop, which is called, we call the stamping distribution, or something that's called a likelihood, which is what's inside the loop, and it says, it sort of generates a data item. Okay, so then the syntax we have for M can either be an instance of one of these model expressions, a primitive model expression rather. I'm going to give you a couple examples in the next slide. Or it could be these index model, which is a way of sort of assembling one model expression from another. Okay, so now I'm going to talk about primitive models and then talk about model expressions, index models, and how we can use them to assemble these complicated models. So here's two primitive models. So first of all, CGaussian, and this is a special case actually for simplicity. So there's two parts to it. So this is like a really simple version of linear regression, if you like. So there's a parameter, a mean, that's outside the loop, that's drawn from a particular Gaussian, and then inside the loop, given the W, well, the W is really the mean, so there's a W.mean missing there. So given the parameter, we do a draw from it. So the result of one Gaussian is being used as a mean for another. Okay, so that's simple. And now a little more complicated. A quick refresher first on some basic distributions. So I want to define some discrete distributions. Okay, and so what's a discrete distribution? Well, they're parameterized by a vector v, and it's what's called a probability vector, which is just a vector of numbers that adds up to 1. Okay, and you can think about a discrete v distribution. It's a bit like an n-sided dice that is going to come up on face I with probability pi. Okay, so for example, an ordinary dice would have a vector of 6 copies of 1 over 6. But they don't have to be uniform in that way, and so that corresponds to the gen. But then so what will often happen is we don't know what that vector v is. We don't know whether it's a fair dice or not. So we're uncertain about what the probability vector is. So a Dirichlet distribution is a distribution over distributions. It's a distribution that will return a probability vector. Okay, and so it's specified like this, and the idea is that well, what would you know about a dice? Well, you'd know how many times it has come up on each of the different sides. So the idea is that you put the counts in, and a Dirichlet distribution with these counts is the distribution, or your uncertainty about what the probability vector is of an n die, given that you've seen CI observations of each of the faces I. So in the case where these are all, I missed out a +1. Minus 1. So actually when there's an off by 1 error here. Sorry about that. So if you poke in 1 everywhere, that's actually the uniform distribution. So that would give you the fair dice. Well, we've not seen any observations of the dice. But after you've seen it come up a few times, maybe it's come up 5, 10 times, and the other numbers 1 each, then you're going to start to get your uncertainty over the distribution has changed rather. You don't think it's a uniform distribution anymore, and you think it's going to be clumped around 10. Okay, I don't want to go into all the technicalities of it, but I hope that gives you an intuition of what the Dirichlet distribution is. So anyhow, back to tabular and the primitive distribution C discrete, its prior over its parameter is given by Dirichlet, where we poke 1. We've seen the idea is we don't know anything about it, how fair it is, so we just put in 1 for each of the counts, which corresponds to not seeing any observations of any of the faces. And then the gen part that actually produces rolls of the dice is just a call from discrete. So those are 2 models. So let me move on to a use of them to do clustering, which is a very important machine learning problem. So it would be like this, that at the end of the day, given this data, I'd like to actually have the machine infer that these guys here, I'd like the machine to do the labeling and say that these guys are one cluster and those guys are in another cluster. And so the way we're going to do that, the way that we're going to do that is this, that we have a model, and it has the XY points, okay? And this particular model is observations of eruptions of the old faithful geyser from Yellowstone, okay? And so there's a sort of waiting time before from the last eruption to the next one, which are on the x-axis, I think. The waiting time is on the y-axis, so that's like 60 minutes, that's 100 minutes, 80 minutes, or whatever. And the durations here are how long the next eruption actually was. And so, this is a sort of famous data set from statistics. And so we'd like to be able to model it. So the actual data you have are these durations and the times. And we have a latent variable that we don't know that is going to indicate which of the 2 clusters the eruption is going to be in. And we write like that. So we use C discrete. So the thing so it's like, it's really, we set n equals 2, so it's more like a coin than a dice. But we don't a priori know what the bias of this coin is. But we set it up like that. So that's going to declare a parameter, which is the bias of this dice between the 2 clusters. And it's also going to produce a sampling distribution that will define, for every row of the table, it's going to define which of the 2 clusters it's in. And then here, we model the durations and the times by Gaussians, using the CGaussian model I showed you earlier. But crucially, we use this new construct of index models, which is the unique thing in Tabular, is that we index these 2, or all 3 of these models, these 2 models here, by the cluster variable. So it might be simplest to put up the chart. So what we get in the end is this, where this line here, C discrete, is declaring this variable. So this is the bias of the coin that we don't know initially. So we just put this Dirichlet distribution on it, which essentially is a, well, we don't know. And then within the loop, the idea is that each cluster variable is chosen by doing a draw, sort of rolling that dice, and which produces that. And then what the effect of this model, of this index expression is that it takes the model here. And remember, the model has got some stuff that's outside the loop and some stuff that's inside the loop. And what it does is it just leaves the stuff outside the loop alone. Those parameters are, other way around. What it does is it makes copies of the stuff that's outside the loop. So a Gaussian would just have a single mean. But because we've indexed it by the cluster variable, which takes values 0 or 1, we get an array of means up here. So we've got 2 different means corresponding to the 2 different clusters. And the same thing, the 2 different, the 2 different clusters. And we do that also for the times. Though in this case, and that's what this notation is showing. That it's a plate, so it's saying there's 2 copies of the material within it. So it's essentially saying we've got 2 copies of the mean variable and 2 copies, of the duration variable and 2 copies of the time variable. And then what the indexed model does for the sampling part is essentially leave it, is run it as before, except we use this expression here to choose which of the, to index the array of parameters, so that it's going to use, so for each data item, depending on whether the cluster is 0 or 1, we use either of the two copies of the duration mean to produce the actual duration output variable that gets observed. So I hope that makes some sense. I have another example, but I've got another example of classification, but maybe I will. So I'll just show you it. That this is what's called a naive Bayes model, and you can see it's using exactly the same kind of syntax. That here we've got each row is an individual, and they're either male or female, and they've got heights, weights, and foot sizes, and some of them are labeled, so males and females, and some of them are not labeled. And so the problem is to predict these. It's a classification problem, and we can sort of use these index models to define a nice this classic sort of naive Bayes model, and it gives some good results. But I'll skip through them. Let me conclude. Actually, taking slightly too long on that. But I guess in this audience I wanted to talk about those index models, and if that's made sense to you, I'd love to talk offline about how those compare to other constructs. Okay, so tabular. I've dived into the details there, but sort of leaping back up, what we've done is taken this technology of machine learning inference algorithms that previously was sort of surfaced in just about developer-friendly programming languages, and we sort of put them into Excel, where we think a lot of data of significance is, and where there's a lot of users who've got a lot of data that they would like to actually work with. And we've done that by exploiting the structure of the data to write probabilistic programs. We have the system. It's ongoing. This is our main project. It's available from this web page. You can actually download it. We've got some internal users. I was really excited. Our user over in Redmond has been running on some vast data sets with Tabular on a 96 gigabyte machine. So, this does actually scale up to large data sets. And I think there's a lot of exciting work to be done on this. So if you're interested, please download it or talk to me. We'd be very interested in your feedback. So thanks for your attention.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.